Okay, so today we keep moving forward with writing the protocol and planning your paper and your analysis. And I want to talk a little bit about descriptive epidemiology and then graphs and tables, because all your manuscripts will contain graphs and or tables, and at least one of these will be descriptive. So I want to talk a little bit about how to do this, do's and don'ts, and there's a little bit of a refresher from previous lectures and a lot of new material as well. If I can, next slide. Right. So when we're measuring health status or disease status, there are three things that we need to take in consideration. The first one is the number who have whatever outcome you're interested in, health or disease, which is the numerator, the population of interest, which is the denominator, and the time period during which these data were collected. We already talked a little bit about this, but when you get into your paper, it's important to think about this, because it's easy to forget it. Because often, and you will see in low quality paper, the use of simple counts. It doesn't really mean anything, you know. I saw 15 patients last month and I saw 20 patients this month. What does this mean? You know, did the volume of patients change in the hospital? There are seasonality, there are all kinds of things. So try and avoid this. Try and avoid using simple counts, and try and always think, if when you present data, it needs to be clear to the reader and to the reviewer how many have the outcome I'm interested in, what is the population they come from, and what time period we're looking at. This is just it's a bit of an exaggerated example to illustrate this. This is the number of deaths from lung cancer in the European Union between 1990 and 2020. Okay, it's not real data, I made it up. So you can see 3 time periods, and you can see, if you're not careful, you will say, oh, you know, in the late 1990s, there were 4 million deaths in the European Union, then it decreased, and then there was a large increase in the number of deaths, okay? However, there is quite a few issues there. Can anyone point them out? The time periods are very different. It's the first thing. Second thing, other thing?
In different periods, like the span of periods from 10 years.
Yeah, exactly. So the first one is 10 years, 3 years, 16 years.
There is no denominator.
There's no denominator. Excellent. And why is this relevant? Because in this time period, the European Union changed, and there were an extra 7 or 8 countries that joined. So the actual population size almost doubled, right? So if you miss that, even if you had similar time periods, it would completely skew the you know, the message. So if you then even if you keep the time periods but actually adjust by denominator, you get to something, a very, very different picture. So it's really important, and you can easily be misled if you're missing this information. So if you're reading a paper, you need to ask yourself, you know, do I actually have all the information that I need to interpret the data correctly? And if you're writing the paper or conducting your research, make sure that you include this, because if you don't, it's actually very difficult for the reader to interpret this. Do you want to lower the right? So when we're talking about the numerator, the other thing that's really crucial is that the case definition remains constant, right? So if you are collecting all surgical cases, you know, all I don't know, bladder cancer cases over a 10-year period, it's important that what is and isn't a bladder cancer remains constant over your time period, right? If you're doing patients with, I don't know, generalized anxiety disorder, don't change the definition halfway, because it will mess up your data. So imagine you have a population here. and we're trying to estimate the incidence of COVID-19 infection in this population, right? And people have two kinds of symptoms. They have cough and temperature, right? If your case definition is anyone with a fever and a cough has COVID-19, and your incidence is 2 people out of 14, which is 14%. If you change one word in your definition and say anyone with a fever or a cough, yeah, your incidence jumps to 50%. And this is important because sometimes even standard definitions change. You know, you may use the, whatever, American Society of whatever case definition, and sometimes they change their case definition because of new data, new information. And if you do that, you need to be aware of that. Sometimes you see big jumps, if you look at, and that can be, you always need to think, what could cause this? And a change in case definition obviously can explain large and rapid changes. And when you conduct studies, it's really important that you are very consistent with how you apply these. And then you need to define the population of interest. Because again, the incidence or the prevalence will change depending on who you are talking about. So, a good example is COVID-19 vaccine coverage in Israel. You see different figures. If you use the entire population of Israel as the denominator, you have about 65–70%. If you use the eligible population, you remove people who are not eligible for the vaccine, it's about 85%. It's a big difference. But often this level of detail gets lost in the papers or in the news, and you will just see, coverage is 70%, coverage is 80%. You think, it increased a lot. No, actually, they just changed the denominator. So you need to define these, and you can define them using a lot of different criteria: geography, age, gender, the health status, or any combination of those. So you need to think, what is the appropriate denominator? For our studies, mostly you have to think, is my denominator the population of the Galil? Is my denominator patient who admitted to Ziv Medical Center? It will make a big difference. And you need to think, there's no necessarily right or wrong, but it's important to discuss this and think about it. If you define it wrong, things can go very wrong. This is data from immunization data from the World Health Organization, looking at vaccine coverage for diphtheria containing vaccine in the Democratic Republic of the Congo in 2018. And you will see, first of all, that each circle is a district. So most district is over 80%, which, if you know anything about the Democratic Republic of the Congo, is highly unlikely. But more interestingly, more than half of the districts have a coverage of more than 100%.
Wow.
Fantastic,
Amazing.
right? Amazing. So
Really amazing.
clearly, there's something wrong with the data, right?
Yeah.
And this can completely mislead your conclusion, because you can end up with reassurance about the health of the population when really, what this tells me is you cannot trust this data. Now, why this happens? Well,
There are Jews in Congo?
there are. I'm not sure. These are generic. Yeah, I'm sure that there is actually there is. There's a yeshiva in Kinshasa, believe it or not. Ken. But this is not the topic of this lecture. So this is how it happens. You have two districts that are next to each other, right? This is not a place where the quality of the healthcare system is good. So there is one kind of good health center in one of the districts, right? So all the people from this district go to the health center to get vaccinated, and all the people from the next door district also go to this center. But because the way the data is organized is not very good, what happens is, in this district, what do? They include people from both districts in the numerator, and then they only use district 1 for the denominator. So you end up with, so again, you need to think about these things. For example, if you are doing a hospital study and you want to know the incidence, or I don't know, admission for whatever condition in the north, right? You will need to exclude patients that are coming to Ziv, but who are resident elsewhere. You know, there are tourists, there are all kinds of, I mean, we have this with the Miyun, for example. If you want to determine the proportion of the population in the north who comes in with injuries, all the tourists that come, you know, during the summer, you don't want to include them, otherwise you will overinflate your result. And the rule of thumb is that all the people in the numerator should actually come from the denominator. If that's not the case, then you have a problem. Right. So what we need, you know, in the very first lecture, we introduced this concept of time, place, and person, and this is really important to describe the distribution of your outcomes of interest. I just want to check that the sound is on. And we also know that the frequency, the basic description, can be made using different measures. We've covered this before. The prevalence, the incidence risk, the incidence rate, and the odds. So in your descriptive tables, you have to think about the numerator, the denominator, the time period you're covering, and what is the best measure to describe it. Are you interested in the total number of cases, the number of new cases? So these are the things to think about. And descriptive epidemiology in itself, before you do any statistics, can be very powerful. And sometimes it's all you need. You know, there is this idea among some researchers that the more complicated the analysis, the better your paper. Actually, you know, from spending a lot of time on epidemiology and statistics, I would say if you're able to show something in very simple ways, without even without statistics or with very simple statistics, this is much more powerful, because all you need is to tell the story that the data tells you. If you start to need and twist and turn the data in very complicated ways, actually, I think that detracts, and it also makes your study less accessible to others. You know, sometimes you will see papers that actually hide behind very complicated statistics because there's not much there. Sometimes you need complex statistics, but if you don't, there's no need. You know, it doesn't make you look smarter just because you use super complicated tests. And sometimes, if descriptive epidemiology is enough, it's enough. You know, I've published really nice papers without a single p-value or a single confidence interval, because the message is very clear, and you need to know what your message is, what is the story you want to tell, and if the data supports that, then that's all you need.
Can you?
Well, of course, you need to think about bias and confounding, but sometimes you can.
Can you give an example?
So an example is a paper that we did at the very early stages of the pandemic. We wanted to know whether the routine childhood vaccination program was being disrupted by the pandemic. So we took the number of doses. This is probably the only time where I used single counts, but I'll explain why. We looked at the number of MMR vaccines distributed in a certain period of time in 2019 and the same period of time in 2020, okay, in a specific location. So we knew that over the period of a year, the population was relatively constant, so we didn't worry about changes in denominator. And we explained in the paper that there were really no other changes to the program that would explain changes. And what we saw is in 2019, the line was pretty flat. The number of doses distributed per month was more or less constant. And then in 2019, you had the beginning, which was the same. 2020. So January, February, March was the same. And then around March, when the pandemic started, you see this big drop in the number of doses. And then you see it coming back up. So, that's pretty, and there was really no, the change corresponds with the event that we're looking at. So when you see this, when you see large changes, you have to think, is there anything else that could explain it? This is why you have bias confounding, and you don't necessarily need a statistic. There's no statistical test for bias anyway. What you need to do is demonstrate in your paper and explain that really nothing else changed apart from the beginning of the pandemic. And people were advised to not go to the doctor except if it was for an essential reason, etc., etc. So and then you saw you saw it going up, and then after that, for a few months, it continued being constant. So the level of confidence we had in the data was sufficient to say that there was a temporary disruption, and then it came back. And then if you wanted to confirm that, you could just continue looking at 2021 data, and you would see that the level was back to 2019. Yeah, so that's enough. You don't need like complex, auto-regression models to show that. It's a description of what's going on. But as Netta pointed, you must, if you do this, you must know and understand your data and the limitations. You must be able to give yourself the reassurance and give the readers the reassurance that there is nothing else that explains, there's no bias, there's no confounding, there's no issues with statistical power, and you need to demonstrate that and explain this in your paper. Okay, this is not about tests, this is about the story. And a lot of this is, a lot of a good paper will explain, the limitation section of a paper is very important. It doesn't make your study weaker. It just shows that you understand your data, you really know the data that you collected, and you understand what it shows and what it doesn't show. So say, I can say this from my data, but we can't say this because we don't really have the data that we have doesn't support it. So here's a few examples. You wanted a few more examples. When do we use descriptive epidemiology in research? Well, you can use it if there is a very unusual emergent problem, like case series, for example, case reports are descriptive. And if something is very serious or very urgent, where the speed is more important than the scientific rigor, it's very useful to monitor disease trends or health trends over time. And it's useful as well to generate hypotheses. Sometimes you have an idea and you're not going to embark on a large complex studies. You want to collect some data and describe it to see whether the description fits your theory, your hypothesis. And then once you generate the hypothesis, then you can test it using an analytical model. So examples, this is I think I showed this before, a case series from the early 80s in California. The first few cases of HIV/AIDS. There's no analysis there, but it's a very important paper, to say, in these hospitals, we're starting seeing these people with these characteristics, so you can see the time, place, and person, and we think there is something going on there. This generates this hypothesis. Then you can go and start, looking into, their immune system status and do virology testing, etc., etc. But the initial description is very important. Simple trends, this is an outbreak investigation that we did in the UK. Number of cases, each day or each few days. There's a little bit of strain typing, but you can ignore that. There's no statistics there. It's just literally the number of cases. But you don't need complex statistics to say that there was an outbreak. The number of cases of hepatitis A increased quite steeply and dramatically, and then went down again. There's nothing. You don't need to know that the number of cases on the 10th of in October 2017 is statistically significantly higher than in August. It is, there's no, this is just the total number of cases.
You also can't have a denominator. You don't know that.
You also no, but you know the denominator because this is in an entire country.
Yeah, but, okay.
Yeah. So this is all cases. Yeah, like yeah. Why is disease trends at the national level or at the regional level? You know,
How does it work in England? It says public health England.
Yeah.
Is that, do they have a different health system from Wales and Scotland?
they do. They do. So there's one for Scotland, one for Wales, one for Northern Ireland. But England is 80% or 85% of the population, so it's a much bigger institute. So you know, reporting the actually this it says rates, it shouldn't be rate, it's actually a risk. The prevalence, oh no, sorry, the incidence of TB in children over the years. Again, you know what your denominator is, the entire population of the country, and you just show the number of cases every week, every year. There's a little, they have put a
Yeah,
confidence
it has to
interval
be,
there.
but it has to be like prevalent because the children under 15, they become not, I mean, they grow up.
No, but this is the number of new cases in this population every year, right? So again, you don't need, you know, you don't need statistics to see that the incidence is decreasing over time. Of course, you can do it, but you have to think whether it's worth doing, whether it adds anything to your message.
Mhm.
Right. So this is about descriptive epidemiology. Now, what I want to talk about is how you communicate your messages and using different tools to communicate. And there's three things that you use in a manuscript. There's the text, there's the narrative, there's graphs, and there's tables, right? And you need to decide what you want to use, which one you want to use. Often what you see is a table, and then the text basically giving exactly the same information as the table, and then the graphing the table. So you have 3 times, this is not, and you don't want this. And generally, if you send this to reviewers, they will say, you know, you're just repeating the same information. So a better approach is to think, when do you actually need a graph? And when do you need a table? The text we'll talk about, we have a lecture on scientific writing, and we'll talk about it. So today I want to focus on graphs and tables. And you can think about graphs as an analog tool and tables as a digital tool. The graph gives you an overview, right? If you're interested in like the third decimal after your measurement, you probably don't want a graph. You probably want a table. Graphs are great to tell a story, to show the reader what is the big message. It tends to be less precise because it's very hard. You know, if you ever try to read the exact value on a graph, it's very hard, but it's very powerful. You know, if you want to show something, and especially in today's world where, you know, a lot of your papers will be tweeted, will be, you know, maybe the communications department of Ziv will ask you for one graph to put on their Facebook page to show your research. The table is much more complicated. You need to get into it, but it's also more precise and more detailed. So you have to think which of those, and you know, often you need both, but you don't want the same information to be in both. You may want a detailed table, and then from your table, you want to think what is the key message? What is the most, you know, if I have one sentence to describe why my study is important, then that's probably the one you want to put in a graph, because a graph is much more accessible for people. So you don't want to put all your table into your graph. And sometimes you need both, and sometimes you need one. You know, I've had comments from papers, you know, that there is this idea that you have to include a table in the graph in the paper. No, it's not the case. If you don't have anything to show in a graph, don't put a graph.
Also, if you have a lot of time points, you can't do a table.
Yeah, if you're doing a time series analysis of trends over time on a daily basis, you don't want to do a table with thousands of. You may need that. You may want to put this as an appendix, for example, which is a different issue because there is the issue of data transparency, and generally it's good practice to provide the readers with the data so that if they want to reproduce the study, they can. You don't want to hide behind your data. I want to talk a little bit about the so-called table 1, the table where you give the characteristics of your patients in clinical research. And this is very important, and it tends to exist in most studies. And this is to convey to the reader the characteristics of the patient. Generally, the purpose of this table is a purely descriptive table. Generally, you can have a p-value if you're comparing two different groups, but it's okay. The purpose of this table is not so it's not your results. It's not that interesting. I mean, if you ever read a clinical trial, it's not the first thing that you jump to. But the purpose of this table is to convince the reader or the reviewer that your groups are comparable with regards to the baseline characteristics. So it's a way to demonstrate the validity of your study and that your results are not explained by bias. So, for example, if you want to compare mortality in two groups, you need to show your readers that, if one group is everyone is over the age of 80 and the other group, everyone is below the age of 40, you're going to see a difference. And you need to show to the reader that this is not the case. Sometimes it is the case. Sometimes they are different, particularly, this is not, we're not in a mostly in clinical trial settings where you can pick and choose and you can have eligibility criteria according to age stratum. You have the patients that you have. So if you have different age groups, then, for example, or different other characteristics, first you need to acknowledge it. You need to say it, not try to hide it, but actually point it out. And you need to either explain the impact of the differences on your study and then do something about it. Either say it doesn't really matter, or do something about it. Let me give you an example of a study we're doing at the moment, and I think you'll see some of these results. We're doing a study looking at whether COVID-19 vaccination is associated with reporting long-term outcomes post-acute infection, okay? So we want to see whether vaccinated people and not vaccinated people report different problems 8 or 9 months down the line according to their vaccination status. It's a real study that we're doing. Hopefully preprint will be out next week.
You have more vaccinated people that are older.
Correct. So because vaccination opened to older people and some of the younger people only became eligible later, the average age is different. And because the average age is different, the baseline comorbidities are different. We have more diabetics, we have more people with hypertension, okay? So there's nothing we can do about it. So there's two things we did. The first one is with the age, we actually presented the data stratified by age. So instead of doing the overall, we did it by age groups. So you're only comparing people from the same age. And secondly, with the underlying conditions, we didn't really have the statistical power to adjust in the model. So we explained that we don't think it actually matters that much. Depending on, because the mostly what we were looking at were things like fatigue, and we said, actually the presence or absence of diabetes as such, if it's well controlled, is probably, it may have a small influence, but it's probably not going to explain huge differences, right?
It also depends
How
on
do you
your
know well
results.
controlled? You looked into disease.
Somebody say that again?
You said well, diabetes is well controlled, then it shouldn't be
No,
much of a difference.
we're making assumptions.
You make an assumption that it's controlled.
It's a limitation. Yeah, these are, this is not hospital patients. This is patients in the. But then you would have to think: would controls be less? Would controls have less well controlled diabetes than cases? real reason to believe that that would be the case. So you need
It
to.
also depends on your results, because if you find in your research that older people with more comorbidities that are vaccinated have less symptoms,
Exactly.
then it even
So
strengthens
this is exactly
your claim.
This is what actually.
If you find that
Exactly.
they're sicker, then you get into
this
a
is why
problem,
you
or
explain
there's no
it.
difference.
This is exactly what we did in the study. We said, look, there are more comorbidities in the vaccinated group, but the vaccinated group reports less problems.
Right.
So what we said is exactly as you say. If the chronic conditions contributed to the reporting, we would actually, if we were able to control it, we would see an even bigger effect.
It's not logical to assume that
Exactly.
it protects you
Yeah.
from
Correct.
comorbidities.
So the bottom line is.
Oh,
The bottom line is you need to acknowledge it, but you need to show this to your readers, right? It's important that the reader understands, have the researchers thought about all these things? Have they taken them into account?
your study is about falling during hiking. Maybe don't protect against that.
Yeah, you're right. But there will be different hikes probably. Right. And then you have, not all tables are descriptive. Some tables are analytical, and this is really important because this is where the nitty-gritty of your study is. It's in the tables. And this is where you communicate patterns and messages contained in your data, where you show the patterns, where you focus the attention on the patterns, and it's the basis for your discussion. So the text around the tables shouldn't restate all the results that are in the table. What it should do is it should use the table as a basis to tell your story, to focus on those results that you are most interested in and that serve your narrative, right? Because generally in table you have tons and tons of different things that you can focus. So for example, if you have, I don't know, a table of incidence of fractures by age group, you don't need to say in the text, in this age group, there were 33% of people that had a fracture in the past 6 months. And in this age, if it's already in the table, you're just saying the same thing. So there's no point. What you want is to give a narrative around it to say, the proportion of injuries increased with age, for example. That is a useful message because you help the reader, you help guide the reader through the data. You're not just regurgitating the data, but the tables is where the nitty-gritty is. Okay, so I want to now talk a little bit about what a good table and a bad table looks like. So this is the basic of a table, and you have really 5 elements there. You have the title, you have your columns with the headings, you have your rows, and then you have footnotes. Okay. So when you write your tables, think about these 5 elements. The last thing you want is to confuse the reader. You've all seen, bad tables with thousands of numbers, poorly organized, where actually it's very hard to distinguish what is an important result, what is not, not an important result. This is not arts and crafts. Don't use different fonts and colors, and it becomes very, very hard to read. So be really boring, simple Arial fonts, no lines. Don't try and put in like dividers and subdividers. Keep it very, very simple. And make sure, this is really important. A good table, you should be able to take out of your manuscript and look at it and understand everything. It should be self-sufficient. Right? So the title, you need to have person, time, and place in the title. You need to know what other patients we're talking about. The row and the column headings, you should explain what the data is. You should specify the unit of measurement. You should avoid abbreviations because people don't necessarily understand them. So if you do use abbreviations or acronyms, put them in the bottom, explain what they are. Okay? And use the footnotes. The footnotes are important to clarify any ambiguities, explain the abbreviations, explain the symbols. If there are inconsistencies in your data, and we'll come back to that, explain them. You know, one of the first things I check as a reviewer is, do the numbers add up in my table? If your numbers don't, sometimes there are very good reasons why the numbers don't add up. But if that's the case, explain why, because otherwise it looks bad. Right? So a few other tips: round your data to meaningful figures. If you're looking at very large numbers, you know, if you if your numbers is in tens of thousands, then you don't really need the decimals. You know, like 136,355.24. This is pointless. Use summary rows and columns if it helps. You know, you may have 1 and 2 and then the total, so you can see the differences. So for example, you may have males and females and total. You want to see whether the how the one category compares to the average. Sometimes it's needed, sometimes it's not needed. Arrange data by magnitude if you have a lot of symptoms. So for example, in the COVID-19 vaccine study that I mentioned, we asked people to report on 20 plus symptoms. So what the reader wants to know is, what are the most commonly reported ones?
You start with
So
the most
organize them in order, either from the biggest to the lowest, not a random order, because otherwise it becomes very hard for the reader to read them. Basically, make it easy for the reviewer, make it easy for the reader, because I can tell you, as a reviewer and a journal editor, if you get a mess, you're not even going to read the paper, you're going to reject it. Rounding, we just again, think about what is meaningful. If you're looking at very small differences and your unit is in microns, then 2, 3 after the decimal is important. If you're looking at large numbers, you don't need that level of detail. It doesn't add anything. It's not meaningful. And make sure the numbers add up. There's nothing worse. If you say there were 100 people in my study, 24 males and 34 females. Where are the others? Are you missing the data? Are there mistakes in your calculation? You wouldn't believe how often. This is the first thing that I check when I read a paper. So here are the tables from the study that I mentioned. I made the table bad on purpose. Don't worry, this is not my actual table. But look, the title. You don't know who are the participants. There's no time, there's no place, there's no person. The numbers. If you look at the numbers, first of all, there's no indication of how many people are in the different groups. You don't know how many people are. If you add the numbers in each of the different variables, they're not the same in each. So where are the ones that are missing? When I'm doing the ethnicity, do I need 2 decimals after, do I really need 2 decimals after the value when describing the ethnicity? Probably not. If you have single digit, don't put a 0. The p-value, do I really need to know, this is highly not significant. 0.7 is probably enough. I don't need 0.751. The more numbers you have, the heavier it looks, and the less likely it is that whoever's reading it is going to look into it well. Stupid things, but look, if the size of the columns are different, which means that the numbers go below, and then it becomes hard to compare, because some things are single lines, some are like two rows. It's just not a nice thing to look at. Okay, wow. Same table, rearranged. So the title, time, place, and person. You know exactly how many people are in each group. You know why. The numbers don't add up, but you know that. And you explain you can't see this. You see I've put a footnote to say actually the number of people answering each question is different. So the numbers are different. The denominator is different in each question, and the denominator is specified. Okay. The other thing, sorry, before. The variables are in the middle, which is really not nice. Left justify the variables, right justify the numbers. Okay, much clearer. So the numbers,
Why
I've-
not left? Why is it
just easy to read.
it's easier to
It's
read
easy to
left
read
and
for,
right?
it's
When the
easier.
numbers are in the right?
Maybe for Israelis, it's different because your brain is used to reading right to left. But in international journals, it's just cleaner like this.
Okay.
Also, it depends on the requirements of a specific journal. But generally, when you send it, when you submit it, this is what I would recommend. Rounded proportions. You don't really need, 37.7. You could actually just do 38 and 62 here. It doesn't really mean much to have 37.73% of
Yes,
female.
42.34.
Yeah, so I've
Religion, like.
exactly. So I've done this one. I haven't done the others just to show you the difference. Look, the p-values are rounded much more neatly. Okay, it's just nicer to look at than this. It's the same data, but it's important because people who read it and reviewers have limited patience. They receive hundreds of manuscripts. If they receive something like this, the message it sends is they're not really
Unprofessional.
unprofessional. Exactly.
Not meticulous.
Correct. Okay, analytical table. So this was a descriptive table. This is an analytical table. So again, the same thing. Right, justify. Try and use a single value per column. So actually, here you could separate the risk ratio and the confidence intervals in two separate columns. It would be even better. Highlight the values that are statistically significant. Put the numbers. Don't just put the risk ratio.
Well, that's great to put the ones that are.
So you put the actual numbers. So
To
if someone
bold the
wanted to
ones that are-
recalculate it, you could recalculate all of these just taking this table without any other material. Right? This is good practice. Okay, so I know it sounds very finicky, but it's really important.
I'm presenting tomorrow a journal club.
Yeah.
About sedation and fasting before. And all the committee, the recommendations are that there's no need for fasting before sedation. And that's the idea. But then in the table, they have a few like high, low recommendations. And then I see that there is a need of fasting before sedation. And I was looking at the table like half an hour trying to understand how can it be that they put it in the table that you need fasting, but the conclusion. And then I saw the headline of that part of the table is not evidence that support that notion. But all the table is recommendation based on literature.
Right.
And this part is the opposite, but it's in the same font. It's very, very confusing.
Yeah, exactly.
Because it does serve the purpose, but you cannot understand it looking at the table.
Yeah, exactly.
So it's very important. Okay, no, I think they made a mistake graphically because it's really ממש לגמרי.
So the bottom line is make it easy for your reader. Don't make your reader's life or your reviewer's life complicated. Always remember what your research question is. What is your story? What is the message that you want to convey? Don't try and include everything. Sometimes in studies you collect a lot of data, and you want to include like every single little result. It's difficult for the brain to process this. It's much easier if you focus on what your message is and then organize your data in that way. You look carefully for mistakes. It's very easy to make mistakes in table. You haven't added the columns properly. You haven't added the rows properly. The proportions don't add up because of rounding. Check all of these things, and this is also why we're here to help. But this is one of the main reasons that papers get rejected, because once you start seeing mistakes, the message you send is the researchers they're not serious. They haven't dedicated the time and the energy that this needs. So spend a bit extra time, read and reread. It's very
Give others to read.
Exactly. Once you get involved into your thing, it's very hard. I would suggest to give it to someone who's never seen it before submitting it, to say, does this make sense? Can you look at this? and I'll guarantee they will spot things that you haven't
It's
spotted.
very difficult for one to give up something he worked hard
That's
on,
true as
and
well.
then maybe something is irrelevant or it's confusing, but for you, it's very difficult to say, I'm not gonna use it.
Absolutely, I agree. The last point is really important. A good table, you should be able to give it to someone and they should be able to understand exactly what you've done and to recalculate your results as well. So the data should be there. Don't give proportions without giving numbers in a table, for example. So this is just a few tips around tables. Graphs. Again, similar exercise because a lot of graphs are not optimal. Again, think about what is your message. And really a graph should have one message. Okay, if you want to say a lot of different things, you probably need more than one graph. Choose the right graph for the right data. There are different, you can do histograms, you can do trends, you can do pie charts, you can do all kinds of things. Again, and we'll talk about when to choose what. Style and etiquette. Again, it's not omanut, right? Don't use 3D. Don't use a lot of use colors judiciously in a way that helps your message. If you want people to focus on a particular group, make this group brighter. Don't use colors that are almost the same on a graph when you have a lot of lines.
Color is, most of the time you print it black and white, so color is problematic. You can have patterns.
This is a good point. Think about this. Often journals ask you this, you should check whether your graph looks good in black and white because people will print it. If all the lines look the same color in black and white, use different colors. You can use patterns as well. Yeah, absolutely. But don't try and make it, there's a lot of things that actually, you think it makes it look good, but actually just distracts, A 3D graph is what a 15-year-old does in a high school presentation. Unless you're doing
sometimes you see it in a presentation, and you see all these, animation and things popping and it seems not serious.
For some fields, it's absolutely. For some fields,
medicine, it doesn't seem like.
you don't want things that.
Serious profession, you can't have that.
No, I think you need to feel the person that talks to you or writes to you is focused on the main thing and not.
Yeah.
in
No, in
other-
a presentation you can put jokes and stuff. It's one thing, but on graphs, you want the reader to focus on the message, not on the.
If you put a joke, it should serve your message.
Jokes in manuscripts, I'm not sure. Jokes in
Not in
presentations.
manuscripts. in
Presentation,
books.
for sure, of course. This is a different thing. This is about communication skills, and you don't want to, but this is not the. Today it's about manuscripts and graphs. If there's no need for a graph in your manuscript, don't put one. Like, don't put something just because you think, I need a graph. No, you don't. And again, focus on what is the key idea to communicate and eliminate the rest. So here's an example. Simple symptom surveillance by region. Okay, what is the message there? There's no message. It's not an interesting. It's not an
You
interesting
have
graph.
a lot of non-relevant.
Well,
It's equal.
yeah. So maybe your message is, there were no real differences by region in the proportion of. You don't need a graph for that. You could be one line in your manuscript. Okay, it's not that informative. Here, weekly number of norovirus tests by week. What is the message? That the negative tests are increasing, that there are many more negative tests than positive tests, that the proportion of positive, you can summarize it in a simpler way. The proportion of tests that are positive. The message is much clearer. There's a single message. Think about how you frame it. What do you want people to focus on? There are different kind of graphs. If you want people to focus on frequency distribution, how often you see something in different groups, then a histogram is a bar chart is a good graph, and you have the height and the width of the bars represents the frequency. So here's an example. Urine iodine excretion, what proportion of patients belong to what group, simple graph. This is an epidemic curve, how many cases meeting a case definition of gastroenteritis by week. So again, you can see very quickly that, you know, in the beginning of July, you had more cases than before. If you want to focus on distribution over time and trends, then a time series is a much better choice. This is what you're talking about. You know, if you have a lot of number of cases per day, for example, then you do a line, you do a trends line. You can show trends, you know, is the things going up or down over a long period of time. You can show seasonality. Do you see more cases in the winter, in the summer? You can use different lines to compare different groups, either different time periods, different areas, different groups of patients. You know, here's an example of a time series. So you have monthly data. This is looking at telephone-based syndromic surveillance for flu by regions in England. So you can see that, you know, in December you have much more consultations for flu, and that there's no real difference by region. It's kind of everywhere in the country. Simple message.
In the corona, we had a lot of these graphs.
Yeah, exactly,
But
exactly.
you could choose one country or see overall.
Yeah.
The habits must be different.
Yeah. This is the study that I mentioned before with the number of vaccines distributed. It's very simple. By week, two different years. So you compare 2 different years. You could see that it's more or less the same until the beginning of the corona period, and then you see a decrease, and then you see an increase because these people who are not vaccinated here are catching up. So, you know, this is probably the best way to, this no stats is published in a journal that has an impact factor of 7 or 8. So, you know, again, you don't need necessarily, you need to think, what do you need to do to bring your message home?
Large numbers.
Yes,
Like it.
correct. This is national data, so pie charts and stacked bar charts, sometimes good. It's less often, but sometimes useful. You know, if you want to show the breakdown of a total in proportion, respiratory virus isolates by type. This is a good way to present this using a pie chart. If you want to look at the relative distribution over time, this is, you know, relevant to you know, why people turn up to emergency departments in different time periods. So your total is always 100%, but the proportion changes. This is a very nice and easy way to visualize
And
this.
then you need to decide which one you put in the bottom, maybe the one
Correct,
you show the trend.
correct.
Like if
So,
that's important
yeah.
for the trend, you say,
The
I have
there's a
more-
downward trend in communicable diseases.
Yes,
I mean, it has to.
no, I mean, if you, depends on your point
It
in
depends
the
what
paper.
what
If
you
you
use.
want to show you have more trauma
yeah,
at the expense of disease,
exactly.
then you put the lower one,
If you're
trauma, and the upper one.
if you're
What I was gonna say is that since we're talking about it's like a zero-sum game, it's a 5. So if something increases and another thing decreases, so so there's a trend in everything.
There's a trend in
course,
everything,
but it
depends
depends-
which one you want to
it
talk
depends
about.
what your study is about.
It depends
your
which
paper-
trend you want to
If
talk
your
about.
paper is about injuries
Right,
and you're a
you put the
trauma
injuries
surgeon,
below.
your focus will be on the injuries. If you are an infectious disease doctor, then you're trying, you know.
And
this
the
is
one
about,
you're focusing
again,
on will be in the bottom because that shows its trend, and of course it's at the expense of
It's
others.
interesting what you're saying, because when I was looking at this, it was like, the green stuff shows the trend.
Yeah.
And then I
same-
noticed the red.
same data, different message. This is why the way you always have to think about what your message is
It's also
and
the
organize
color,
the data
with the color.
in that way. Yeah.
The green decrease, it seems decrease because the blue is almost the same, but if the blue change too,
Right.
then the one you put in the bottom is always starts in the same place, then you see the trend best clearly. So I think, I don't know, but the one you want to focus on, the trend you want to focus on should be in the bottom in a clearer color, not clear, but more obvious color.
Yeah,
And then the
exactly.
others,
Yeah. It all
so
comes
the fact that they go lower because of that.
it all comes down to framing what your message is and organizing your data and your tables according to that. Okay. horizontal charts versus vertical charts. If there is no logical or numerical order, then you're better doing horizontal bars that are horizontal. If your variable is, if there are categories that are, either numerical, there's a logical progression.
Sorry, when do you use the horizontal?
You will see this in a second. So, for example, answer to a questionnaire. Why do people not vaccinate? Okay, there's no real there's no specific logical order, right? It's just categories. So it's easier to read if you organize them in this way for this particular type of response. So if you have a questionnaire with and you see they're ordered in decreasing order, so it's very easy and clear to read. If you have a logical order, level of education and vaccine coverage, okay? So it's not a numerical variable, but your categories, there's a logical progression from no education to higher education, okay? So you'll notice that there's no axis, but it's organized as a vertical bar chart, okay? If it is numerical data and there is, it's a continuous variable, then you do put an axis, even if it is categories. But again, it's a logical order, right? So all these things are little tips, but it makes your paper nicer, the flow nicer, and ultimately, when your paper is competing with a lot of other papers, it's nicer for the reviewers and nicer for the editor. So let's try and take a bad graph and make it better. Okay, this is a bad graph. Why? It's very hard to read. You have two different things. Are you interested in the differences in these different categories? Are you interested in the time trends? You can't even see the thing below. It's made up data, but why are people not swimming? Okay, so you see, this is a nice piece of art, but it's not a very good scientific graph. The first thing is, what are we interested here? And if you look at the data, there really isn't a very clear trend here, right? It's pretty constant. I mean, there's a peak here. We'll come to that. But broadly speaking, there's no real difference in between years. So
you reorganize.
Yeah.
The like you said,
horizontal and by year.
Yeah, and whatever, but you can see the trends. You can see the trends, like downward trend with, I don't know, whatever, or a steady trend, and you can't swim, and then you have fear of jellyfish.
You
can do it horizontal, and each year, but in flat.
Yeah.
And each year has a different color, or each reason has different color.
Exactly.
Either you go.
So
depends what you want to show. If you're interested in the trend over the years, then you do each year in a different color. If you are interested in the reasons, then I think each reason has its color.
Exactly. So here I would argue that actually
trend within each.
Having what you're interested in here is why are people not swimming? I would argue that there really isn't within each specific reason. No, within each reason, there isn't a lot of change year on year, right? So maybe you don't need the year. Maybe you can do an average for the whole time period, because it's not that informative, right? So here what you can see as a first step is that the proportion of response, the reason for not swimming, is more informative than the change year on year. If there's a small differences year on year, but no clear trend.
But you had some differences within the groups in the years, and maybe something happened. I don't know. Maybe there were more. The purple is jellyfish. Maybe there was an attack of jellyfish 2012. So
correct,
because it stacks
so
like that.
If you look within each category, the only one that really sticks out is the jellyfish, right? So
you can do another graph.
We'll see in a second. So we've seen this one. Now we said there's no logical order to these categories. They're just categories response. So you can flip the chart and organize it by order of magnitude. Yeah. And then the 3D doesn't actually makes it harder to read. Are you looking at this point or this point? Okay, it's becoming clearer. Okay, and you're absolutely right. The jellyfish thing was sticking out, right? So maybe that's a different graph. Maybe specifically for jellyfish, you are interested in the trend to know what happened in 2012 that
Someone
that
got
explains. Maybe there's
hospitalized because of it.
or maybe global
Massive.
war. Maybe the currents change. I mean, who knows? Okay, but it's a different message. The message is different. The message here is, the leading reason for not swimming is the temperature of the water, and the message here is there was an increase in fear of jellyfish between 2011 and 2012. They don't belong in the same graph.
So, I mean, but if you had other data, then there would be an influence on the relative importance of each graph, right? So if there was more people, a greater proportion of people that fear swimming, and you have an uptick only in fear of jellyfish, then so that means that they should look for a reason or whatever.
Of course, yeah. And then, this could also be, this is descriptive data. This could be a reason for, looking into, this is a hypothesis generating. So that there's an increase in fear of jellyfish. Why is that? Maybe there was a movie about giant killer jellyfish, well, who knows? But you could look into the reasons, as a different study. Okay, we're almost done. I want to talk about, continue a little bit with graphs, but I want to talk about telling your story with the data, because you can tell very different, you can present this, you can have the same data and have very, very different looking graphs, depending on what you want to say, depending on what scale you use, on absolute and relative measures, on rounding, and whether you use ratios and
With
differences.
the scale, I think one should be careful, because you can really prove your point with scale, but some people may think it's manipulation.
You have to be careful.
Because you can cut the graph like it will seem
Well, look at this.
with a meaning. Like
Okay.
this.
What is the
That's
top?
a manipulation, because it starts from 86%.
Exactly. But it's
So
the
there's
same.
no difference, but it looks
It's
like
the
there's a
same.
huge
Well,
difference.
is there a difference or not? It depends. It depends
When
whether
you cut it.
look. This is the proportion of children fully vaccinated for DTP vaccine. Okay. There's two messages you could bring. You could choose to say, really, in Israel, in each region, there's not a lot of difference, or you could say Jerusalem is under vaccinated compared with the other. It depends. It depends if you think that 1 or 2% difference for vaccination is important or not.
It's not what you think, it's what's.
Well, it depends.
If 1 or 2% change in vaccination rates changes the possibility of the disease to spread, it does have
Exactly.
meaning. If in epidemiology, 1 or 2% doesn't make a change, or maybe those 1 or 2 is the cutoff where 86
Exactly.
protects and 88.
So you take measles, for example. If you have 96% or 93%, it's actually different, because
Right.
with one you're not reaching the WHO's standard, you have a risk of outbreaks, and with the other you don't. So I agree that it can be a little bit manipulative, and people use this, pharmaceutical companies use this
Right.
all the time. It doesn't mean that it's wrong to do this. I mean, it's good practice to do this, but if it's important for you, if your message is, we need to have an intervention in Jerusalem to increase childhood
Then
vaccination.
you need to put a line where,
Yes, maybe
where you
you
want to
could
be
put a line. There's different ways, but
above and
what I
below
wanted
line.
to say is, if you're not careful, you can, and there's psychology in there. If you see this, you will immediately draw your attention to there, maybe not on the axis. So look in those things carefully, and when you do your when you write your study, think about these things. And if you do use a scale that doesn't start at 0, be open about it. Don't. It's not about trying to mislead. This is not fake data. It's
I
very
would do
real.
the upper one, I would do horizontal from high to low, and then put a line where is the limit I want to be above. And
That
then
sounds
you
like a
see
great graph.
which places are below,
That's
which places are
justifying-
above, and then which one are close, which one are very far, and you
I
get
agree.
the bigger picture.
Absolutely.
This is like, when I see the upper one here, it seems manipulative, like someone wants to show Jerusalem is not good enough.
I agree.
But if you put it like that, and then you put the line, like above and below OECD
Absolutely.
rates of doctors per.
Absolutely,
and then you see all the
absolutely.
countries.
Correct.
You know where you are.
Proportion changes versus absolutes. This is also a real study that we did. We wanted to know whether offering pertussis vaccine in maternities increased the vaccine coverage. So we looked at the time period before the maternity vaccination was offered and after. And you can see in the areas that are offering the vaccine, the proportion of change is much higher and statistically significant than in the area that isn't. Great intervention. But if you look carefully, if you actually look at the values, you're starting from a much lower base, and you end up with a lower vaccine coverage than in the other one. So of course, if you start with a lower base, smaller increases will lead to, in relative terms, higher. If you go from 1 to 2, that's a 50%, that's a 100% increase.
100%.
Exactly. So it is easy to, and I agree with you that it can be manipulative. The important thing is to be transparent. I think if you didn't put this, it would be manipulative. But here you give the reader all the information, and you need to think, what is the important thing? Am I interested in the study in the absolute level, or am I interested in the impact of the intervention? Which is it?
And then you can discuss it.
Then you can, and you need to discuss it. You need to discuss it.
And the N is so small.
What is the N is small. I mean, these are large areas with each of them has hundreds of thousands of patients. But yeah.
Oh.
But if you did this would be, if you didn't put the actual proportion, it would be manipulative. You need to focus on your message, but you need to be transparent with your reader and your reviewers.
I'm having a hard time understanding this table. So the bottom line is the clinics where they offered vaccination.
Yeah.
Actively offering.
No, so the vaccine is in everywhere. Vaccine is offered in the Rofe Mishpacha.
Okay.
In this one, in addition, you could also get vaccinated in the maternities. Yeah. Could be that these were.
And it's not before and after.
It is before and after. Yeah. So in the first part,
No.
both places only
Before
offered in the
in the
Rofe Mishpacha. In the after, the top only offered in the Rofe Mishpacha, and the bottom also in maternities. Yeah. So it's not a very convincing study, but you could, you could make it more convincing depending on how you.
But it is interesting. I mean, you have to find it interesting that the percentage before they offered additional vaccination options, there's such a big difference.
Yeah.
So you can ask yourself, where did we add these? Is there a bias to with regard to where we start offering
Could be,
additional?
yeah. So it could be that
Maybe they started offering because it
exactly.
was.
So they actually offered it in the areas where the coverage was low to begin with.
It didn't start with a study. It started with a decision from the ministry.
So it's all these things are part of the discussion, but you could see how you could present the data in different ways. If you wanted to say, if your message was offering vaccination in clinics in maternities is a great thing, or if you think if your conviction is it's not a great thing, it's a waste of time, you could present the data differently. So everyone have their own biases as well. Absolute versus relative. Okay, this is data that I made up. Association between rare brain tumors and living next to a high tension electricity line. Okay, so prevalence per million in the no is 4 per million and 8 per million. Okay, so you can say your chances having a brain tumor when living close to a line is 0.008%. You could say 99.999% of people who live next to a tension line are cancer-free. You could say living by attention line is associated with a 200% increase in brain cancer. All these are true, right? But you can see that the message is very different. And the reader, the reader will either interpret this as, oh, it's quite safe to live next to your attention line, or it's very dangerous to live next to your attention line, right? So they're all true. The data is the same. So you need to think about what your message is, and you need to think, and the other thing here is you have to think whether you have to understand and convey the difference between statistical significance, because here, the results are statistically significant, and public health importance. A doubling of an extremely rare event remains a very rare event. So you have to think, what is importance? Is it the increase, or is it the actual value? So yeah, maybe it does increase it, but the risk remains extremely low. I mean, this is not real data, by the way. I just made this up, but it just shows you that depending on how you present it in your table, in your graphs, you can convey a very, very different message, and you need to think about that. And I agree that there's a fine line between having a message and being manipulative, and you don't want to be manipulative. What you want to do is
You want to be
offer
perceived as manipulative.
No, you want to offer your interpretation because you interpret the data based on your experience and your expertise, but you want to give the reader all the data so that he or she can make also their own decisions. This is why it's really important to actually give the data. If you only set a 200% increase without actually giving the numbers that are very low, that is manipulative. If you only giving the numbers, this number without a baseline, that is being manipulative. So you need to give the tools to the reader and the reviewer to be able to understand how your thought process. And rounding as well, you could round, you could say actually in all areas, the prevalence of brain cancer was lower than 0.05%. Also true, seems very low, but it's not quite the whole story. So there's really a whole art and dark arts of tables and graphs. The descriptive part of your study is really important. We talked about this. It either tells a story by itself, or it gives the reader and the reviewer the confidence that your study is valid. Choose your tools carefully to tell your story. Think about, do I need a table here? Do I need a graph here? Sometimes you need both, not always. Don't duplicate the same, don't have the same data 3 times in your text, in your graph, in your table. That's a waste of time. Make it easy for the reader. Make your tables and your graphs clear. Have clear and simple messages. Make sure there are no mistakes. And the data is what it is, but how you convey it is subjective. So think about what your communication objective is. Be transparent. Be upfront about the limitations of your data. Give your reader the tools they need to decide whether you are being transparent or whether you're being manipulative. And that's it. Stop the recording. Oops.
Breakfast is served in the kitchen.